Hi everybody.
We are going to review how the operating system virtualized CPU. In the screen, you can see the file cpu.c. There is a main loop and there is a printf statement within the main loop. Print statement prints out the string supplied by the user, and because it is inside the while loop of infinite loop, it prints the string forever, unless it is stopped by the user. There is one function spin1, and let's see what it means. Let me switch to this command file. There is a spin function. It gets the current time, and it continuously calls get time so that a certain amount of time has been passed since it is called. And a certain amount of time it has to check is supplied by the user, and the parameter name is how long. Let me get back to the original program. Okay, this is the function, and let me compile and run this program. Okay, I just compiled it, and I'm going to run it with 3 parameters, A. So this program prints out the string AAA in 1 second interval forever. So if I want to stop the program, then I have to bring it to the foreground, and I have to type Control-C. Now, let me execute the 3 copies of the CPU program. To do that, I do CPU A, CPU, another instance of CPU, another instances of CPU, and the third instances of CPU. Now I'm going to supply the CCC strings to the CPU. Okay, let's run the program. Why don't I run it in the background? So we're going to see that 3 instances of CPU programs, and then each program prints out its own supplied parameters. In the screen you can see that one program prints out AAA, the other program prints out BBB, and the third program prints out CCC. And these 3 programs runs forever. Even though we have 3 processes running, they seem to run completely in parallel with their own CPU hardware. That's the role of the operating system. Hi everyone. This time we are going to look at mem.c, a program that prints out the contents of the memory and the associated address of the memory. The mem.c, there are important statements here printf. It prints the process ID and then value of a location that is pointed by p, and p is a pointer right here. At the beginning, an operating system allocates an integer to this variable, and then it prints out the values whatever there. And then for inside the iteration, every time it iterates, it increases the value of pointer by 1. Let's load the program. We first have to compile it, of course. So we are going to compile the mem.c, and then we are going to run it like this. So it shows the process ID and then address of the pointer variable, and then we show that the contents of the address pointed by p increases by 1 for every iteration of the program. Now we are running the 2 instances of the mem program. I'm going to execute the 2 copies of mem program. As you see, the processes are launched. Let me just first briefly stop the program and explain how the meaning of individual figures and fields. Okay, so this is the process ID of the first process, and the second one is the process ID of the second process, because they have been created back to back. So the second process ID is the one greater than by the process ID of the first one. Okay, so this is the address of the address that is pointed by p. This is the address pointed by p of the second process. even though they are pointed by P, clearly the values in these two locations are increased independently. So this is two process ID that ends with 89, and this is the process ID that ends with 90. And each value pointed by P increases by 1 independently, as if they are allocated the separate memory address space. So one of the important roles of the operating system is provide a separate address space for each process. And we just observed how the operating system guarantees the isolated address space for each process. Let us explain the role of concurrence control in operating system. In the screen, you see the function, you see the file called thread.c. It contains two global variables. First one is counter, and the second one is loop. And then there is a function called worker. And in worker, it increases the counter by the number of times that it specifies the loops here. If you look at the main program, there is some function, a certain function you have never seen before. The name of the function is pthread_create. It is very similar to the combination of fork and exec. Meaning of this statement is create a thread, run worker, and returns. The main program creates two threads, and each of the threads executes worker function. And worker function increases the counter variable by loop number of times. So if the loop is 10, the two threads increases the global variable counter 10 times each. So we expect that the final value of the counter variable reaches 20. The problem here is the nature of the thread. Thread does not have its own separate address space. It is different from process. Here you see the two threads. The two threads created by the main program share the same global variable counter and loop. The thread program creates two threads, and each thread increases the counter variable by the thread parameter. So if you type 1000, then the counter variable will increase by 2000 times. What about we increase it by 100,000 times? Oops, there's something wrong. In the course of accessing the shared variable, these two threads compete with each other, and they override. Instead of increasing the value of counter from what the other thread has increased, they apparently override the increased value updated by the other party. In concurrence control, operating system has to ensure that when a thread accesses a variable, the access is completely protected from the other accesses from the other threads. That is the role of an operating system. We're going to review the role of an operating system in managing the storage device. You see a simple function. The name of the file is io.c. It opens a file and writes a hello world to the file and close the file. That is it. So the 13 means the length of the hello world and null character string. So we write a hello world string to the file just we have opened, and then we close it. That's the role of this program. So this is what we do when we want to store the contents of something to the disk safely. Let's look at the code. So we are going to compile the code. Yes. We just compiled it. Before we run the code, let's review that if there is a temp.file exists. Okay, so the /temp/file is the destination file which we want to save the contents. So there is no such file or directory. Now I'm going to execute the program which is compiled. Done. Then let's see if such has file created. Voila. So we have just created file. And what is the contents of the file? Let's look at the contents of the file. Hello world. So we successfully saved the contents of the string you want to save to the file named /temp/file. The important roles of the operating system is to maintain the data safely on the disk.